Okay, get ready for this, because it sounds like something straight out of a sci-fi movie. Imagine trying to see the furthest corners of the universe. Not with some giant billion-dollar satellite, but with a swarm of drones flying in perfect formation. It's a wild idea, but it's at the heart of a really fascinating research proposal that we're going to break down right now. But first, you might be asking, why do we even need an idea this radical? Well, it all comes down to a problem that's been bugging astronomers for, just a few centuries. Getting a sharp, crystal clear photo of a distant galaxy is incredibly difficult. But why is that? For the longest time, we've really only had two ways to deal with this problem. And honestly, neither of them is perfect. They both come with a pretty serious catch. It's a classic pick your poison kind of situation. And here's that trade-off right here. On one hand, we can build telescopes on the ground. They're way easier to get to and fix if something goes wrong. The problem? We have to look through our planet's atmosphere, which is like trying to read a book at the bottom of a swimming pool. It's all wobbly and blurry. The other option? We go to space, like with Hubble or the James Webb. You get a perfect, pristine view, but it costs billions, with a B, of dollars and can take decades to build. So what if? What if there was a third option? A way to get above all that atmospheric fuzz without the mind-boggling price tag of a rocket launch. This is where the research out of Manchester gets really cool. They're proposing a concept that tries to give us the best of both worlds.
Let's break this down, because the name is a mouthful. A UAV swarm-based mirror array. Think of it like this. It's a flying, shape-shifting telescope mirror. You have a whole fleet of drones, and each one is carrying one small piece of a mirror. They fly way up into the stratosphere, and then, poof, they arrange themselves into one single giant mirror to collect light.
So how would a mission like this actually play out? Well, it's basically a four-step dance. Step 1, the whole swarm of drones takes off. Step 2, they climb and climb way up into the stratosphere above most of that blurry air. Step 3, and this is where the magic happens. They organize themselves into a perfect parabolic curve, just like the mirror in a regular telescope. And finally, step 4, they get to work, observing the cosmos as one single unified instrument. Okay, so we've got the what, we get the concept, but the real question is the how. I mean, how on earth do you get dozens of individual flying robots to act like a single, high-precision optical instrument? Well, it's an incredible engineering puzzle, and it really breaks down into 3 main challenges. First up, you have to design the drone itself. Using 3D modeling software, the researchers are basically creating the perfect little platform to carry a super lightweight carbon fiber mirror. But the real trick, the secret sauce, is keeping that mirror absolutely still while it's flying. That means you need sophisticated systems to damp out any vibrations, plus tiny little gimbals to make micro adjustments on the fly. Okay, so you've got your drones. Next, you have to get them all to dance together. An advanced control algorithm acts as the swarm's collective brain. It uses GPS and other sensors to know exactly where every single drone is, down to a tiny fraction of an inch. What's so cool about this is that it makes the whole system super resilient. If one drone has a problem or drifts off course, the algorithm just tells the rest of the swarm to shift around and fill the gap. It's brilliant. And the final piece of the puzzle, making sure this flying mirror actually works like a telescope. Researchers use some really specialized software to trace the path of light rays as they bounce off all the little mirrors. They analyze something called the point spread function, which is just a fancy way of asking, how sharp is the focus? Basically, can it tell the difference between two stars that are really close together? The whole system is designed to correct for tiny errors and then fuse all that data into one amazing, high-quality image. Now, I know what you might be thinking. This all sounds fantastic in theory, but is this real? Could it actually work? And that is a totally fair question. It's exactly why the researchers are using intense, rigorous simulation to test every single part of this concept before they even think about building a physical prototype. This right here is the digital proving ground. They use something called computational fluid dynamics to see how the drones will handle the thin air and winds of the stratosphere. They use finite element analysis to put virtual stress on the drone and its mirror to make sure they won't break. And, like we just talked about, they use optical ray tracing to predict exactly how good the final picture will be. They're testing everything in a virtual world first. And look, this isn't just some weekend project or a vague idea. The research lays out a structured 2-year plan. It moves step by step, really methodically, from doing the background reading and building the computer models, all the way to running simulations and optimizing the design. This is serious science.
So let's just dream for a second. Let's say the simulations all check out and this technology actually proves to be possible. What would that mean for us? What's the big picture? Well, this could do more than just change how we look at the stars. It could completely change the kind of questions we're even able to ask about the universe.
The potential impact is just massive. For starters, it would be radically cheaper than a space telescope. And it's scalable. If you want a more powerful telescope, you don't build a new one, you just add more drones to the swarm. This could totally democratize astronomy. Suddenly, universities, smaller countries, organizations without massive budgets could get access to space-quality views. And more eyes on the sky means more chances for incredible discoveries.
And when I say cheaper, I need you to brace yourself. The estimated total cost for this whole initial 2-year research phase, we're talking hardware, software, prototyping, everything, is just £15,000. Now, compare that to the $10 billion it took to build and launch the James Webb Space Telescope. The difference isn't just big, it's absolutely staggering. The researchers themselves, they know how huge this idea could be. Don't just take my word for it. In their own words, right from the paper's introduction, they call this a potentially transformative approach to observational astronomy. They're not talking about a small improvement here. They're talking about a fundamental rethinking of how we build a telescope in the first place, which really leaves us with this one final, fascinating thought to chew on. For pretty much all of human history, our greatest views of the cosmos have come from single, giant, monolithic machines. But this research asks a totally different question. Could the future of astronomy lie not in one giant eye on the sky, but in a coordinated, intelligent flock of tiny robot eyes? We'll have to wait and see.